For over a century, physicists have been intrigued by the idea of black holes, with the concept gaining traction around 1916. These cosmic anomalies are among the most captivating and enigmatic phenomena we know, sitting at the intersection of vast gravitational forces and a peculiar invisibility to our understanding. A black hole, potentially weighing as much as 2 to 4 million times the mass of our Sun, remains a mysterious presence in the cosmos. Despite decades of intense research, our understanding has expanded from almost no knowledge to piecing together more details, with even more discoveries being made recently. A breakthrough by M. Yakubu has revealed startling insights about the interior of black holes, which may challenge our long-held assumptions and offer new perspectives on the nature of these celestial bodies. This new information makes it possible to look into things that might have been overlooked before. Join us as we venture further into the fascinating world of black holes and uncover what's hidden within the universe's vast and inspiring expanse. But what exactly are black holes? Before we delve into the latest findings by Yakubu, it's essential to revisit the basic understanding of black holes. While most of us have at least a general sense of what a black hole is, there are still some key elements that remain unclear. In 1916, Albert Einstein's groundbreaking theory of general relativity predicted the existence of black holes. At that time, the notion was purely theoretical. Black holes are real objects in space, but it wasn't until about 50 years later that evidence was found to prove it. This revelation came in the 1960s during studies of the star X1, a luminous celestial body emitting X-rays. Observations showed that these X-rays were not just randomly moving, but were being drawn into a dense, invisible mass. This mass, later identified as a black hole, changed our perception of the cosmos. The discovery was huge because it proved that black holes were real, elusive things that needed more research and weren't just Einstein's imagination. Following this groundbreaking discovery, scientists worldwide began a global quest to uncover more about black holes. Their efforts led to the realization that the Milky Way alone may host around 100 million black holes. Though due to the challenges in detecting them, this estimate remains imprecise. Even though black holes are incredibly difficult to pinpoint, scientists believe that millions of these massive entities are hidden within our galaxy, making it even more crucial to understand them. Let's break down the core concept of gravity. Black holes exert such immense gravitational forces that anything entering their domain is squeezed into a singularity, a point where the laws of physics, as we know them, cease to function. To put it more succinctly, black holes resemble enormous vacuum cleaners that draw everything inside of them. One of the most terrifying aspects of studying black holes is that if someone were to fall into one, they would gradually stretch out and become a singularity, their body torn apart by the intense gravitational forces before the point of total destruction. It's best to avoid getting too close to one, though they are scattered across the universe. Even though it is nearly 500 light-years away, the proximity of the nearest black hole still raises valid concerns. In 2021, scientists achieved a historic milestone by capturing the first clear image of a black hole, the M87 black hole. This achievement was the result of numerous nights spent taking photos and aligning them to create a single, cohesive image. As more data was gathered, researchers were able to discern that black holes consist of 3 distinct layers, contrary to the common misconception that they are just endless voids. The first of these layers is called the event horizon, which marks the point beyond which nothing can escape. Once something crosses this boundary, it is inevitably drawn toward the black hole. The second layer, known as the photon sphere, is where light itself gets trapped, unable to escape due to the powerful gravitational forces at play. The singularity, where all matter is compressed into an infinitely small point, is the final phenomenon, a place where the very fabric of reality collapses and all known laws of physics break down. What's even more intriguing is that each black hole is unique in its own right. While they follow the general three-layer structure, the way they behave can vary significantly. This makes them particularly challenging to study, as conventional scientific methods don't apply. To study black holes, scientists have no choice but to investigate these anomalies through indirect means, such as observing the radiation emitted from them or analyzing the gas and dust swirling around them. Sending a probe directly into a black hole is an exercise in futility, as anything that crosses the event horizon is inevitably pulled toward the singularity, where it is crushed into nothingness. This unavoidable fate means that billions of dollars cannot be spent on probes that would meet their end before offering any valuable data. Consequently, researchers are left to study black holes in 2 dimensions, despite them being 3-dimensional singularities. Adding to the complexity of black hole research is the fact that no 2 black holes are identical. When studying them, we must account for the breakdown of physics as we know it. Black holes may emerge as a result of massive stars collapsing into one another, according to some theories about how they formed. As a star burns through its fuel, it can no longer produce enough energy to counterbalance the inward pull of gravity, leading to its eventual collapse into a black hole. If the star is massive enough, this process continues until the collapsing matter becomes a singularity. NASA researchers focused on the M87 galaxy, which is located at the center of the universe, in order to gain a deeper comprehension of the characteristics of black holes. There, they observed a powerful whirlpool of hydrogen gas spinning at mind-boggling speeds of 1.2 million mph. The centrifugal force should have caused this gas to meantime fly apart, but instead, it remained intact, suggesting the presence of a massive object at the center, likely a black hole. This object is believed to weigh up to 3 billion times the mass of our Sun. Another significant theory was proposed in 1963 by New Zealand mathematician Roy Kerr, who used Einstein's equations to describe the behavior of rotating black holes. He argued that system, rather than collapsing into a point as previously thought, a rotating black hole forms a thin, ring-like structure known as the ergosphere. This rotating disk of matter is key to understanding the breakdown of physical laws in the vicinity of black holes. Kerr's model also predicted the existence of an Einstein-Rosen bridge, a theoretical wormhole that could provide a shortcut through space-time, connecting distant regions of the universe or even parallel universes. To grasp the idea of a wormhole, it's important to understand the concept of space-time as described in Einstein's theory. Space-time is a fabric with 4 dimensions that is warped by massive objects. This warping creates gravitational fields that influence the movement of other objects. Think of space-time as a piece of paper. If you fold the paper, you create a shortcut between 2 points. This shortcut is the essence of a wormhole, a passage through space-time that could connect distant locations almost instantaneously. Although wormholes are a theoretical concept and no direct evidence of them exists, they are a natural consequence of general relativity. However, wormholes are inherently unstable, meaning they would collapse quickly if created. Despite this, the idea of a wormhole as a potential gateway to different parts of the universe, or even different points in time, has captured the imagination of physicists for years. The CR wormhole, named after Kerr, is a particular kind of wormhole that has attracted a lot of interest. This hypothetical wormhole could theoretically connect 2 distant points in space-time, possibly even linking different universes or timelines. While the idea of using wormholes for interstellar or time travel is exciting, there are significant challenges to overcome. To begin with, creating or stabilizing a wormhole would require exotic matter with negative energy, which is not known to exist in significant quantities. Additionally, the immense gravitational forces and tidal effects near a wormhole would likely destroy any object attempting to pass through. Despite these obstacles, the study of wormholes remains a fascinating area of theoretical physics, offering tantalizing possibilities for understanding the universe and its mysteries. It is anticipated that wormholes will be unstable, and it will be nearly impossible to safely traverse them due to the extreme radiation and forces that surround them. Critics argue that Einstein's equations, while useful for understanding gravity, do not account for the quantum forces that govern radiation and subatomic particles. A new theory is required to fully comprehend wormholes and black holes, one that unifies gravity with quantum mechanics. This theory, often referred to as the theory of everything, is a quest that many physicists, including renowned scientist Michio Kaku, have pursued for years. Superstring theory, which proposes that subatomic particles are in fact tiny vibrating strings, is one promising candidate for this theory. The theory proposes that these strings create the universe's fabric, explaining not only gravity but also the phenomena surrounding black holes and wormholes. However, superstring theory also demands the existence of additional dimensions of space-time that are so small they cannot be detected using the technology currently available. Despite the challenges, the pursuit of understanding black holes, wormholes, and the fabric of space-time continues to captivate scientists, offering the potential for groundbreaking discoveries that could reshape our understanding of the universe. Continuing from where we left off, the pursuit of superstring theory and other theories that aim to unify the forces of nature is an ongoing challenge, but it holds the promise of unlocking new insights into the very nature of reality itself. These theories propose that the universe is composed of more than the familiar three dimensions of space and one of time. In fact, they suggest that additional dimensions exist, but they are so minuscule and compact that we are unable to observe them directly with current technology. However, their existence may hold the key to comprehending phenomena such as black holes, wormholes, and the universe's deepest mysteries. Superstring theory offers a fascinating picture of the universe, proposing that all matter and forces are manifestations of tiny vibrating strings. These strings have the ability to vibrate at a variety of frequencies, with each vibration representing a distinct particle. Just as a guitar string can produce different musical notes based on how it vibrates, the fundamental particles of nature might correspond to different vibrational patterns of superstrings. This theory would not only provide a unified explanation for the fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, but also open up entirely new perspectives on the structure of the universe. If proven, this theory would also open up new avenues of inquiry. This could possibly shed light on some of the most pressing issues in physics, such as the nature of dark energy and dark matter, which together make up the vast majority of the mass and energy in the universe but remain largely a mystery. Superstring theory, despite its beauty and potential, has not been demonstrated. The fact that the additional dimensions the theory predicts are so insignificant that they are beyond our current observational capabilities makes it difficult to test the theory. To detect these dimensions, we would need instruments of unprecedented sensitivity and precision, and even then the evidence might be indirect. This makes superstring theory a challenging subject to test through traditional scientific methods. Nonetheless, it is one of the most compelling ideas in theoretical physics due to its mathematical beauty and coherence. At the same time, scientists are also working on other approaches that might lead to breakthroughs in our understanding of black holes. For example, quantum gravity is another field of research that seeks to combine the principles of quantum mechanics, which govern the behavior of subatomic particles, with the theory of general relativity, which explains the behavior of large objects like planets, stars, and black holes. By combining these two theories, it is hoped that researchers will be able to gain a deeper comprehension of the quantum mechanics of gravity and the nature of black holes and other cosmic phenomena. The intersection of quantum mechanics and general relativity is especially crucial when studying black holes, because the extreme conditions near a black hole's event horizon, where gravity is extraordinarily intense, demand a theory that can account for both quantum effects and relativistic effects. In fact, the singularity-filled interior of a black hole is one of the most bizarre and extreme environments in the universe. The singularity represents a point where space and time become so warped that the usual laws of physics break down. Understanding what happens in such a place requires a theory that can reconcile quantum mechanics and general relativity. This has led to the development of ideas like loop quantum gravity and other quantum gravity models, which aim to resolve these contradictions and provide a more complete picture of black holes. One thing is certain. As we continue to investigate the mysteries of black holes, we become more aware of how much there is still to be discovered. The more we learn, the more we realize the complexity and potential of black holes. Black holes are not only places of destruction, but also places of incredible complexity and potential. Whether they are gateways to other dimensions, as some theorists believe, or hold the key to understanding the deepest secrets of space and time, black holes remain a crucial area of study. As our tools and theories evolve, so too will our understanding of these enigmatic objects. Looking ahead, the next major challenge will be to refine our methods of observing and studying black holes. One of the most exciting advancements in recent years has been the development of gravitational wave astronomy. Gravitational waves are ripples in space-time caused by the acceleration of massive objects, such as the merging of black holes. By detecting and analyzing these waves, scientists can learn about the behavior of black holes and other celestial objects in ways that were previously impossible. The detection of gravitational waves has already provided groundbreaking insights into the dynamics of black hole mergers, and future experiments are likely to yield even more revelations.